So my talk is about the inner regions of protoplanetary disks. And so this is the outline of my talk. First, I'm going to go through a very brief introduction, and then I'm going to talk about the inner disk in terms of continuum observations, so the dust, and then a little bit about the gas and my conclusions. So this is just to remind you what is my definition of inner disk. So it's pretty similar to the one of Jorik. So it's everything that is within 5 AU from the central source, so very close to the star. And actually, because of these small spatial scales, we cannot resolve the inner disk using direct imaging. And actually, even with instruments like a sphere, this inner disk is usually within the coronagraph of the observations. So this region is very interesting, even if it's challenging to observe it. Because in here happens many things that affect not only the inner disk, but the complete structure of the disk, of the full disk. So in here we have accretions and winds that will dominate the gas dispersal and drive the disk dynamics. We have also dust particles evaporating at the dust sublimation front there. And we have enormous amounts of radiation in the form of energy, in the forms of ultraviolet, optical, and infrared radiation that will determine the full energy balance of the disk. And I want you to take a closer look to this picture here, because I want you just to remind that in the inner disk we have like two sorts of components. So we have the dust-free disk here where the dust cannot survive. So this is my gaseous disk. And then we have the dust disk and the rim or the dust sublimation front. That I will mention these terms later, so just keep them in mind. So what do we know about the inner disk? So most of our knowledge about the inner disk is based on indirect tracers, because it's so difficult to spatially resolve this region. So in the past, what people has done is to study the spectral energy distribution of Herbig's and T-Tauri sources to derive rough estimates about the temperature and perhaps something about the dust composition of the inner disk. And regarding the gas, what many people do, apart from studying the accretion rates using lines, they also have studied forbidden emission lines to trace the presence of winds in the inner disk. So the lines like this, the oxygen forbidden line at 6,300 angstrom is characterized by complex profiles, and sometimes you see that the low velocity component can be derived into a broad component and a narrow component that is associated with the presence of winds. So while, however, these indirect tracers, as I call them, so that means not spatially resolved observations, can only give you global constraints. But if you want to really constrain models, what you need is to have direct tracers, so spatially resolved observations, and that unfortunately can only be done using optical interferometry. Alexander gave a very nice introduction about interferometry, so I'm going to skip this. Just to let you know that in this talk I will mostly talk about results from the VLTI with the instrument gravity and a little bit about Pioneer. And what I will use is the term called baseline, that is the distance between two telescopes. So with the interferometry, what we get is not the spatial resolution that you can reach with one of the telescopes, but what you get is the spatial resolution equivalent to the distance between the two telescopes. So, with this plot, I want to show you that we really need optical interferometry, so we cannot go to the inner disk using ALMA. First of all, because the inner disk is hot, so you will not be tracing much with ALMA, but also because the beam size is, even with ALMA, with the longest baseline, is too big to trace small structures in the inner disk. So you need to go to optical near-infrared interferometry with instruments like gravity, even better with CHARA. Unfortunately, until very recently, interferometers were not very sensitive, so we had to wait until Pioneer and now also with Gravity to get statistical surveys of the dust components of the inner disk. These are reconstructed images done with Pioneer for the continuum, and what they found is that there is a variety of morphologies in the inner disk that perhaps might resemble what is found in the outer disk as well, but of course the spatial scales are much more smaller, so it's difficult to find details. And what we find is that the geometry of the inner disk in the continuum can be well approximated by ring-shaped morphologies, but very, very wide. What else can we tell about the continuum in the inner disk? Well, in interferometry, the ones that are expert in interferometry will know about closure phases. So this is an observable for interferometry, and it gives you an idea of the asymmetries of the system. And now here I'm showing some of the results found with the statistical survey for gravity on the continuum. And what we found is that for most of the erbic sources that we have sampled, the closure phase is relatively small. So I think that the average closure phase for the full sample is 10, 11 degrees. And very few objects have closure phase signature larger than 30 degrees. And this means that the continuum emission is pretty much symmetric and smooth. This, because most of the near-infrared emission comes from the rim, what it also tells you is that the rim is pretty smooth. So it's not a vertical wall, because it will give you huge closure phases that in general, we do not observe. Another thing that you can find using interferometry is that you can try to get an idea of the dust temperature and composition of the dust grains in the inner disk. And for the sample sources, what we find is an average temperature of the dust of around 1,500 K. So this is more or less the sublimation temperature of the silicates. And in general, the sources are between 1,400 and 1,800 K. This is the sublimation temperature of the carbon. And by correlating, even if this is difficult because there is a great degeneracy between the grain composition and the size and the rim position, but you can try to find what type of grains do you have in there. And this has been done by Lucia Klarman, that is a postdoc in Heidelberg. And what we have done is, or she has done, is to try to understand what sort of grains in terms of composition and size do you need to fit the rim position. And so this is the average rim position for the Pioneer and Gravity survey. So most of our sources are located in here. And what it means is that in order to reproduce this, you need a multi-grain population. So our conclusion from this is that the rim seems to be white and smooth and is consistent with a multi-grain population. Unfortunately, we are still missing a similar study, that's the one that I showed you for the continuum, but on the gas. And in truth, this is one of the main aim of the Gravity YSO survey is to look at the gas. So in our YSO GTO program, what we want to do is, apart from studying the continuum, is to also to try to spatially resolve the hot bracket gamma line components and the warm CO, the vibrational lines at near-infrared wavelengths. And with that, we want to try to prove the presence of winds in the inner regions of circumstellar disks. What do we know, and what I'm talking about winds here? This comes from an early studies that we did with Larissa and Vladimir when I was in Bonn. We tried to model our interferometric observations with AMBER. AMBER was the first generation of interferometric instruments for the VLTI. With some models, but first I want you to remind what it is, what you are seeing here, because unfortunately we do not get images, as Antonella pointed out, but we get these ugly things that are the spectra of the line profile. So here the bracket gamma, then the visibilities. The visibilities give you an idea of size of the object. Differential phases. The differential phases give you the photocenter shifts of the line with respect to the continuum, if you're measuring that, and the closure phases that I mentioned before here are close to 0. And just to remind you, when you get a visibility that is 1, is a normalized quantity. Visibility 1 means that you are not resolving the source, so it's a point source. When it's 0, it means that your object is fully resolved. So using the model that Larissa described before, that it includes the continuum emission from the star plus the disk, and line emission that comes from a disk winch, or if we need it, a magnetosphere, we were successful at modeling the AMBER high spectral resolution observations of these two Rebeca stars. And what we found is that most of the bracket gamma line comes from a winch, located pretty close so within the dust sublimation radius, because as you can see here, the visibilities across the line increase, and that means that the lines is emitted in a region that is more compact than the continuum. So it's compact, but it's extended, so we can resolve it. So we thought that these are winds. Why is it important to detect these winds in the inner disk? You know that now these non-ideal MHD simulations have shown that the turbulence and the magnetorotation instability in the inner regions of protoplanetary disk could be suppressed, and instead they are launching these MHD winds that apparently remove very efficiently the angular momentum. So by trying to prove the presence of these winds, we might be also trying to get an idea what is the angular momentum transport in the disk and whether turbulence or MHD winds work, and in which sources it works and what not. But doing the type of simulations or the type of modeling that I showed you before with Larissa and Vladimir is too expensive in terms of time. So and Larissa cannot model for me 24 hours, 365 days per year. So I thought, okay, we have to do this quicker in a different way. So the idea is to try to understand, by only measuring the size of the bracket gamma line using geometrical fitting, whether this line is compact or extended. If it's compact, especially for the case of the Rebecs, because they have very compact magnetospheres, it will mean that most likely the emission comes from something that I'm not able to resolve, most likely the magnetosphere. If it's extended, then there is a good chance that the line comes from a winch, and then I will be able to resolve it. We use this first approach on the Tauri source SCRA north with some commissioning data with gravity. Here I'm just showing you the visibilities. We couldn't detect any large differential phase or closure phase in this source. So here you see the bracket gamma line and then 6 visibilities because we have 4 telescopes. And what we see, as in the case of the Rebecs that I showed you before, is that the bracket gamma line comes from a region that is more compact than the continuum. Then by doing geometrical modeling of the continuum and the line emission, what we find is that the continuum comes from a region that is around 0.11 AU from the source, but the bracket gamma emitting region comes from something that is much more smaller, of around 0.06 AU in size. That is around twice the size of the expected truncation radio for the source, so that is 0.03 AU. So the idea for the source is that even if it's a T-Tauri source, and we really believe that the magnetospheric is there, and that there can be a strong contribution to the line from the magnetosphere, a large amount of the brachydgamma line comes also from extended emission from a wind. So what happens with the rest of the sample? So the bulk of the sample of gravity for now is airbics, because they are bright, we can observe them with the auxiliary telescopes. And what we find is that in general, as we saw for the other sources, the brachydgamma line is more compact than the continuum, so it's located well within the dust sublimation radius, and it has a typical size of a few milliseconds. But I was filling in these dots in this plot when Vladimir told me that my talk was from Thursday to Monday, so I stopped putting dots. What we find is that, so this is a size of the brachydgamma line, so the blue dots are the size for the brachydgamma line, the open diamonds are for the continuum. So you can see that for the few sources that I plotted here, the brachydgamma line is more compact than the continuum. And at a certain point, and this was already observed previously by Richie Kurosawa, but for a small number of sources, and here I haven't included NWC297, that is also big. What you can see is that at a certain point, the size of the continuum and the size of the brachydgamma coincides. So I'm not sure yet what it means, and I have to populate this. So for now, I have to stop doing random plots and focusing on the correct luminosities. Is that there might be that you are seeing a change, perhaps, on how the matter could accrete, for instance. So here, for these objects here, low luminosities, it could be that you are seeing magnetospheric accretion, but for these other objects where you see that the size of the continuum and the size of the line coincide, it could be that we are tracing a boundary layer, optically thick, so you cannot distinguish the emission from the continuum and the line. In any case, for the objects that we resolve the brachydgamma line, the size that we derive is much bigger than the expected size for the magnetosphere, because the magnetosphere is a point source in the case of the airbags. Because I have time, I think. I have time, right? So I wanted to show you also some results about the CO, because as I told you, we also wanted to study the work component. So here I'm showing you just a shot from the observations of 51 off, where we see the low vibrational bandhead emission in the CO, and we have pretty nice data with the visibilities for the 4 bandheads and the differential phases for the line, so it's A-shaped and really nice. We have more than one epoch. So Maria, she is still a PhD in Dublin, but she will be moving to ISO soon. This month, I think, yesterday. So what she did is to first apply a geometrical model for the visibilities of the CO. So the red points are the CO, pure line visibility, so without the continuum. The squares are the star plus disk contribution, and this blue line is the size of the disk. So what you can see is that the CO is very compact and is much more smaller than is located very well within the sublimation radius. And because we had these nice differential phases, what she did is to apply a COLT model to fit the revibrational bandheads, and also apply the intensity map that she gets from the COLT model to reproduce the differential phases that we measure in 51 off. So she was able to find a good match, and the very interesting thing, or I think is very interesting, is that she has derived a size for the CO of around 0.12 AU, and with a temperature of around 2,400 K and a column density of around 2 times 10 to the 21 centimeters to the minus 2. So at the beginning I thought, how is possible that so close to an airpeak you have this temperature, and it's because one has to think that in this region there is no dust. So it's just the gaseous disk. And if you go to the old models of James Muzzerole and Calvet of the inner gaseous disk around airpeak stars in LTE, there is a very good agreement between this temperature and what they expect for this inner gaseous disk. So, and with this I finish, and I leave my conclusions back.
Concerning the plot that you have shown about the size, the bracket gamma region and the luminosity of the star, it reminded me a bit of this similar correlation between the near-infrared continuum size and the stellar luminosity. That, if I remember well, it also break for the 30
Yes, they are under-luminous, yes. The B stars are less luminous than you would expect. So they do not go like that, they move down.
So, can you comment on that? So we have smaller inner rings, dust rings, but larger gaseous pieces, something like that? Or?
What I'm thinking about the boundary layer is that I'm not an expert in boundary layers, but I would assume that they are optically thick. So I think that we cannot, you confuse the optically thick dust-free region and the dust continuum. I can make you a sketch.
I just have a comment on that, because I was wondering if it means, in fact, that what we are seeing as a continuum in the near infrared is not dust, but it's a kind of a free bound-free emission. Because then you will have more or less.
Yeah, we have to check that. We have to check that for the people. But I have no idea.
That, I don't know if anyone has done that.
I don't know.
Sorry, you twice said the word boundary layer. The star for which you showed this has size, radius of the boundary layer 8 milliarcsec. Yeah? It was written in the table.
Oh, okay. Did I write that? In this one? No, these are
No,
this one.
not here. Not here. 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 Here.
Oh, okay, yeah.
What is physical distance?
This is a full width maximum, so the radius is half. So it's 4 milliseconds, and I don't remember which one is this one, but I don't know. Put it.
Boundary layer is a region where you have rotational velocity and Keplerian velocity and magnetic field strong enough at this distance.
No, for the boundary layer, what I mean is the old models where the matter was just accreting, like spiraling in without going to the
Yeah, but you should have rotation radius. And what is
I don't know.
physical distance?
I don't know if in a boundary layer you have a hole, and then you, perhaps Larissa can help me with that. I think you just accreted until you reach the surface of the star.
Yeah, so you say that the star has radius 4 milliarcseconds. Yes?
Yes, so what it is.
You don't have to look. I mean, I'm not sure, again, I have no idea. I haven't seen any model of this boundary.
No, I do not know how they go.
But do you have to see the emission just from the stellar? Suppose that you reach the star. Why should you just see the emission from the stellar radius? It must have a width, although it cannot be zero. It can be small? You think it has to be very, very small? It cannot be a factor of 2 or 3?
I don't know.
I know.
We need more models, yeah, of boundary layers.
Anyway,
I have one short comment. The interferometric observations based on the infrared region of spectrum is very important for many reasons, but one of the reasons is the determination of the inclination of the inner disk.
Yes.
But in all models, it is assumed that the unit source of radiation, infrared radiation, is a disk. This is correct in the case of the Herbig I stars, but this may be not correct in the Tauri stars, because in this case, the source of infrared radiation can be the disk wind, as it follows from the model by Benz and Konigsberg. Therefore, it is important to check the contribution of this additional source of infrared emission when you model the interferometric observations of Tauri stars.
Yeah, but we have not modeled yet anything.
I think you are
Geometrical
pretty much
fit.
ahead of the models in
Yeah.
a way. Because, first of all, most of this information comes just from what is called geometrical models.
Yeah.
You fit a ring or a Gaussian or something like that. No, correct me if I'm wrong, I'm not an interferometer.
No, you are right. Come on, she says
So
this.
you don't make any assumption on what is the model in a physical way for the continuum. Inclination comes from the continuum, not from the line.
Continuum, but I speak about continuum emission of the disk wind. Continuum
Yeah, but I mean, what you are saying is that we cannot assume that there is just a geometrical model. We have to model a complicated structure. I mean, different fraction of the continuum coming from a wind, from the disk, and all of that. That is well ahead of what one can do in most of the stars.
But the disk is not the unit source of
What we
continuum
measure
emission.
is you fit a ring or a Gaussian. No?
At least for the air,
And you don't know what it is. If it fits well, you say, well, more or less, it has this size, this inclination, this position angle.
Yeah.
And that's why also the error bars are very large, and we are still arguing about misaligned disks. No?
Yeah.
I don't think one has done that with lines or with anything else, as far as I know. You can correct me.
I think in Exeter you published a paper with a disk winch that was lifting grains. Wasn't you? I have to check. Yeah, for the source of the continuum emission. Yeah. No, it's-
Well, we have to move on, but there'll be a little bit of discussion section at the end. Maybe at the end, we have a little bit of discussion section. Okay, let's take the speaker again.
Stefan, I think one of you were in the